Hello, so my name is Allaire. I'm going to be presenting you accuracy, performance, resources trade-offs in RISC-V microarchitectures for genetic programming. So this work was conducted inside of IETR from CNRS in Rennes, France, with partnership the Università Polytechnica de Madrid, and it was published in Computing Frontiers 2026. So the first question that we're going to be asking is why do we need co-design? So tangle program graphs, which is the algorithm in the study here, is a genetic programming algorithm introduced by Stephen Kelly's PhD dissertation, which has the properties of being accurate and light, and in addition of its adaptative complexities, meaning it is able to adapt itself through the complexity of the problem that it's solving. Additionally, we want algorithm to be performance, meaning having quick reaction times. Here we are targeting nanoseconds inference. And we want our systems to be as low cost as possible. So here we are targeting below $1 off-the-shelf components without hardware acceleration. And to reach all of those objectives, what we do is that we rely ourselves on algorithm architecture adequation, co-design methodology. So the study here tries to map genetic reinforcement learning models, so tangle program graphs, on embedded systems that are ultra constrained. We have 15 tangle program graphs and 18 microarchitectures under study. And this yields trade-off in terms of accuracy, performance, and resources. So we have both an algorithmic design space and an hardware design space that are structured and come at interplay. So the methodology developed here is for the co-exploration of TPG and CPU microarchitecture. To this purpose, we develop an evaluation flow that gives us the accuracy, performance, and resources. And this allows us to perform design space exploration on this three-dimensional axis and select a set of non-dominated solutions that will fit the designer need. So this presentation is going to be talking about the background and state of the art of tangle program graph, as well as CPU design space exploration, discussing the evaluation methodology that we propose, our results, and discuss those results. First, tangle program graph, as its name proposes, is a graph of program. So to understand the tangle program graph and what it does, I'm going to just be running you through an inference. So the inference starts from the root team. It then computes every program along its way. The program leading to the highest value, program compute value, that are displayed. The program computing the highest value is the one chosen. We then continue the progression of the traversal along this path. We find ourselves on a new team, which also computes all of its program until we find the highest value. And when we reach an action, we know that the inference is over. The action here is the action to realize on the learning environment. The learning environment here is a robotic arm. So it presents itself as this little robot, which have joint angles that are used by the tangle program graph programs to do its computation. So we can see here that it's observed the value of alpha, beta, and delta to do its computation, and uses some instructions, so here exponential, addition, multiplication, to output some values. And those values are used in the graph to traverse it. Through a mechanism of reinforcement learning made of observation of the learning environment, here the robotic arm state, the tangle program graph finds some action to perform, performs the action, which will actualize the arm states, and through this mechanism, the tangle program graph learns. Here in this learning environment, the starting position of the arm is fixed, the target is randomly generated, and we have some fixed obstacles as well. So at the end of the training of the TPG through reinforcement learning and genetic programming, we find ourselves with a fixed graph. And this is on this fixed graph that we want to do the fastest possible inference. So the literature in genetic programming has shown that the instruction set plays a big part. So here in this study performed by Desmond Seol, we can see two TPGs that were trained on the Frostbite Atari game learning environment, over 400 generations shown on the x-axis with two different instruction sets. We can see that the pink instruction set is simpler than the orange one, which has access to cosinus, logarithm, and exponential functions. And the result of this is that the accuracy of the orange instruction sets is higher. Using different instructions has an impact on the cost. Here we can define a hardware agnostic measure of this cost. What I mean by that is that the cost of executing an instruction always depends on the microarchitecture that you execute it on. So what we do is we try to take a step back and give a hardware cost that is independent of the microarchitecture. So this was proposed by Crary et al. And what they do is that they define a Mach equivalent cost of performing the instruction. So for instance, we can see that sine and cosine are 4 Mach, tangents cost 5, exponential 11, and natural log 12. Those are for approximation libraries that were developed using polynomial methods. And the idea here is to have an interplay between those instruction computational costs and the microarchitectural design of the chip under consideration. So we saw that for the genetic programming instruction sets, the GPIS of the TPG impacts both accuracy, performance, and energy consumption. In training, it means different expressive power for the evolutionary search of the genetic programming, impacting the accuracy, and for the inference, it means a different computational cost, impacting the performance. The data type, for the data type of our machine learning algorithm, we can follow the same idea. It's really used in deep reinforcement learning, where they use quantization to leverage lower latency at inference, smaller model size, lower energy consumption, and all of that are gained through trade-off of the accuracy. This is really useful since some embedded systems are equipped with single precision floating point units. So for those, we don't need to perform the quantization, but most are not. And you really need to have this step of trade-off. So now, just a bit of background on CPU design space exploration. The idea here is to use a microcontroller called XIP. It's a template microcontroller. It allows us to fix some components of the microcontroller. So for example, all SOC-related components, such as memory size, bus topology, bus addressing mode are fixed. We don't touch it. And we explore components of the microarchitecture of the CPU. So here we use 3 microarchitectures and the inclusion of an FPU. The idea here is to use the microarchitecture design to drive the computational capabilities. So our evaluation flow will first be detailed by focusing on the training accuracy, by the training side, and which leads to the accuracy of the model. So we first structure an algorithmic design space. So for instance, here we have single and double floating point precision data types on different instruction sets, which are using addition, subtraction, multiplication, division, and comparison. Then we can add logarithmic and exponential function, trigonometric, and mix those. We can follow the same strategy for fixed points with 16 bits of precision. And here we differ only for the last 3 instruction sets, where what we will do is approximate logarithm and exponential using bit shifts. Yeah. So this algorithmic design space is made of 15 Tangle program graphs. Now we test the expressivity of those GPIS, those instruction sets and data type from the robotic arm learning environment. So on the x-axis, we have the different combination of instruction set and data type that gives us the 15 Tangle program graph. On the y-axis, we have the distance to the objective. So the robot started from a fixed position and it reached a certain distance to the target objective. So here, the initial distance is approximately 300 millimeters. So we can see three families of color, which are the different data types used. Here we have double precision and single precision, which are roughly equivalent in terms of accuracy. And we have the fixed precision, which is largely dominated. If we normalize the accuracy, it's dominated by around 5%. Interestingly enough, we can see that these instruction sets yields the highest accuracy for fixed points, and it also has the lowest computational cost because it doesn't have multiplication or division or any logarithmic or trigonometric functions, meaning it's a really interesting design point for co-design. Those results are pair learning environments, meaning you have to retrain every Tangle program graph for each learning environment, meaning this methodology is extremely computationally intensive. So this is the first part of our design flow, where we select some instruction set and data type and train the TPG, yielding some models. Now we will focus on the synthesis part that gives the resource cost of the microprocessors. So we now structure an hardware design space using the two-stage microarchitecture from open hardware, which is roughly comparable to the ARM Cortex-M0. This is used as baseline for study. And the four-stage open hardware CVE4, which is roughly equivalent to the Cortex-M4. And from those two microarchitectures, we vary some internal mechanism that I will present to obtain 18 microarchitectures. So the hardware components that we vary, as we've seen, are the pipeline stages, depth, the register file depth, being our only memory, and the multiplier latency. So those give rise to compromises between performances and resources. So as an example, here we use the CVE2 as a baseline, configured with the lower number of registers possible, no multiplier, a two-stage pipeline, and no memory, no cache memory. We just have the S static RAM for code and data section. This represents one microarchitecture, and then we can synthesize all those microarchitectures on an FPGA and place them. And using a resource cost function that is custom to FPGA synthesis, so it's based on digital signal processors, lookup tables, and flip-flops, it gives us different resource costs. Those resource costs are then used to compare the microarchitecture internals between themselves. And our baseline here is at 100%. And we can reach difference of up to 157%, meaning we have a 57% difference between the costly 4 stages microarchitecture with floating point units and the 2 stages microarchitecture without multiplier. I forgot to mention that this is the 4-stage part, and this is the 2-stage part. I redirect you for the paper to see in more detail what this means. Okay, so now that we have defined microarchitectures for the computation and the genetic programming models, we can do simulation to obtain the performance. So we identified 368 valid mappings and performed the benchmarking of Tangle program graph. So here our objective is to obtain a fair benchmarking methodology. So just to guide you through our methodology, the objective is to be fair, meaning that some TPG will exit very fastly after only a few computation, while others have to do a lot of computation. So what we do here is that since this is GS, we consider an equiprobable graph where each team has the same probability of being traversed. And this is how we measure the TPG latency. Now that we have the microcontroller generated by XIP on the right, the trained TPG using JGLATI, and then generated using the code generator, we will compile for the appropriate RISC-V targets and simulate the execution on the validator simulator. And this gives us one inference. We do 736,000 to have the performance of our different points. So this gives us our entire flow, which is composed of, on the left, the training, on the middle, the compilation and simulation, and on the right, the synthesis of the different microarchitectures. And those results yield solutions on the 3D Pareto front. So we have one dimension, which is the performance in clock cycles on the left, one dimension, which is the resources cost of the different microarchitectures, and one dimension, which is the accuracy of the solution. We first have a TPG front with an accuracy of 30 millimeter in distance to objective. A second with slightly lower accuracy, but it's non-dominated since it's better in terms of performance and resource. The third follows the same idea. It has lowest accuracy, but better performance, and the fourth as well. So what we can see in this 3D design that was projected on 2 dimensions is that for 2 TPG mappings here, we have a first mapping with the star that uses an instruction set that is really heavy. It has trigonometrics, logarithm, and the second doesn't have those functions, meaning it's going to end up being less accurate, but 1 order of magnitude faster. We can follow the same idea with the fixed point TPG represented by the square. It's 1 order of magnitude faster than the cross TPG, and comes at the loss of 4% in normalized accuracy. So that means a total of 2 orders of magnitude difference in performance. Another interesting region is the use of an FPU. So on the costly floating points data type with trigonometric, the FPU does not reach very interesting performance, but when using multiplication and division, the FPU internal mechanisms allow it to reach a throughput that is competitive with the simpler instruction set, meaning the FPU will compensate by having a higher throughput. Additionally, we can see that there are some interesting design regions, such as this point in red, which is a 2-stage micro-architecture without any multiplier, without divisor, with only 16 registers, and it has about 300 cycles latency, which is really comparable to the latency of the 4-stage microarchitectures located here. So this is the 4th stage. So that means this design point is a really good candidate. To conclude, we propose a co-exploration methodology that gives us accuracy, performance, and resource trade-off for genetic reinforcement learning models on ultra-constrained embedded systems. The proposed evaluation flow structures both an algorithmic and hardware design space evaluates the mapping on the simulator and analyze the design space. And this gives us TPG on the CVU2 core, which achieves about 300 latency inference without hardware acceleration. Floating point units is shown to be made superfluous when selecting the right instruction set for the TPG. And we can see that the instruction set with the lowest computational cost can have the highest accuracy among its data type. Limitation and future work include proposing a framework where we do not rely on cycle-accurate simulation anymore. The objective of this is to account for the frequency of the design, because here our design space is a bit biased by the fact that four-stage design have lowest critical paths than two-stage, so the frequency should favor a bit higher peaking stage architecture. And full simulation here makes our design flow really expensive, so we could build surrogate models to estimate the TPG latency at inference on a given CPU without doing full simulation. Okay, thank you.
Question in the room or online?
Yes, please. Could you go back to the 27? Before the graph, yes, it's fine. I didn't understand where is the accuracy axis.
It's in blue.
In blue. Okay, so it's a good candidate with a red square is lowest accuracy.
Compared to the two fronts that are above it, it has an accuracy that is lower, but it has latency that is much better, which is why it's still on the Pareto front.
Okay, thank you.
And this is the same for this front compared to this one. This one has a better accuracy, but a much lower latency.
Okay.
Any other question? Online? You were hearing us before, don't ignore us.
I have one resources is one axis. How did you count resources when we have DSP memories and
we did a linear combination of the factors. So what we do is that we consider the baseline here as a cost of 21,000 LUTs and 28,000 flip-flops. We normalize to this. And then we consider that the DSP, which are not included in the baseline, should be half of LUTs and half of flip-flops. Okay, it's a cost function, but then when we evaluate this cost function, we have the purple trend. And if we define our cost function as the total available resource on the FPGA, we have 1% of difference between what we define and the total resources, meaning it follows the soft core CPU trends on FPGA. This is not to be compared directly with the gates on an ASIC. It's a soft core comparison for CPU and FPGA.
On your title, you said that you were going to do this study on RISC-V.
Yes.
And what is the impact of being on RISC-V on your study? And could you extrapolate, generalize what you have seen? Is it the cost of the functions?
No,
like logarithm?
No, the RISC-V is the instruction set of the architecture that we used. The architecture that we used are open source, and the RISC-V instruction set architecture is open source, and we have access to the definition of the instruction set architecture, so the assembly instructions, meaning that the architectures that we used from open hardware are based on this ISA. So here it was the definition of the RISC-V ISA allowed those hardware architectures to be freely available and configurable. So this gives us a framework to work on. If we had worked on ARM Cortex M0 and M4, we would have had only 2 microarchitectures and possibly not access to the microarchitecture system Verilog, which we have access here. So this gives us more margin to work with.
Okay.
Yeah.
User question? You haven't talked about energy here?
Yes. So I haven't talked about energy. I think we can consider, given the literature, that the CPU that we are using are really simple. They are 2-stage and 4-stage. So we can consider that the power variations are really small between, for instance, so the 2 biggest differences are going to be between the load of the instruction, loading from the memory, and computing. But even between those instructions, we can say that it's average. And if we take the average power and multiply it by the latency, we are going to have end up with the energy. So we could say that the power consumption is pretty stable compared to other more complicated microarchitectures where you need to power gate some parts to access the computing part for a short amount of time, and then come back to the control part. So I would say the power is pretty stable, and if we were to find the average power cost, we will have the energy cost.
Yes. Okay, thanks for speaking again.
Thank you.